Today we're going to continue our discussion of logic gates. The next logic gate is the AND gate. The AND gate has the symbol like so, where A and B are the inputs and the out is the output. The proper term for this is the state table. Is A, B, A times B, low, high, low, high is low, low, and high. So the state table, if the A and B are not both high, the output is going to be low. In Boolean expressions, the AND is similar in nature is treated similar in nature to the multiplication. So if you were to look at the state table in this way, in binary, where a 1 represents the high state and a 0 represents the low state, you can see 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is 1. So you can look at it mathematically as being a multiplication. Now that holds true for just about every case. We'll get to another case later in Boolean, when we get into Boolean algebra, where it does not behave like multiplication, but for the most part, the AND gate behaves like multiplication. So you can, in Boolean expressions, see A star B, A dot B, or just A B, just like you would in a math class for multiplication. So you can, all these three are the same. So you can use any of those three notations. Just use them consistently throughout your documentation, so as to not cause confusion. But A star B, A dot B, or just AB. When you look at the actual schematic of it, what's going on internally is you have your power, or DD, a resistor, two transistors going to ground, and these are your A and B. And the output goes to another transistor, and that is your out. Actual implementation uses a little bit different configuration, but this will work. The idea is if A and B are both low, these transistors are turned off and power will go out through here. Okay? This, if you recall from last time, is an inverter. So if both are low, if both these are low, the output here would be high. Then you have to invert it to make it low, to match up with low, low, low. If either one of these transistors is low on the input here, the power will go out like this, be inverted, and then go out low. If both these are high, then it creates a short circuit, drawing this low to ground. This will be low. And then power will go out here to make the output high. Pretty basic setup that we'll get to in next week. We'll get to what happens when you do not include the inverter in the AND gate. But this, like I said, is one of the three basic gates. Let me go ahead and erase this. And I'm sorry? Oh, okay, I'm sorry. Oh, okay. I just erased a couple of resistors. Good now? All right. How this sort of thing can be used is if you have three inputs that you want to AND together to make sure they're all together, three ANDed together, A, B, C, and C, you can link them together with two AND gates, like so, and that will behave the same as a three-input AND gate. You can feed the output from one into the input of another, and then have the third input going into the second AND gate, and make it a three-input AND gate. They cascade together well that way. Another use for it is, say you have a data line and a select if the select is high, or if the select is low, the output is low, and if the select is high, it follows the data input. So if you want to select whether or not the data goes through a certain point, you would use an AND gate to have the select line. If the select line is high, whatever's on the data line will be out in come out the output. If you look at the state table, if data is your B line and select is your A line, you'll notice that if the select is low, the outputs are going to be all low. If the select is high, the output matches the data line here. So that is a data selector. And, now, if you when you go to use the everybody got this? Getting there? Okay. When you go to use this in Digital Logic Lab, you're going to use, I believe it's the 7408 chip. And like the inverter, it's a 14 pin integrated circuit. Where you have four AND gates in the package. And 1, 2, 3, 4, 5, 7. And that is the pin configuration of the integrated circuit. This notch in the chip indicates the orientation of the chip. There will be a physical notch in the top of the chip on one end of it. And this is, like I said, I hope I'm getting this right. The 7408, the XX indicates the technology used to manufacture the chip. But the 74, it's going to be either 2 or 3 letters. But the 7408 indicate that that's the part number. You might need to use a magnifying glass to see the numbers printed on the chip. But yeah, they're pretty small. I forget how wide the chip is, but the pin the distance between the pins is 0.1 inch. That's called the pitch. Is 0.1 inch or 2.54 millimeters. So they're pretty small. They get smaller, but and again, like the inverter, you have to connect to the power and the ground, or the chip will not work. So let's see here. What other stuff is the AND gate used for? We'll get into other uses as we learn more logic gates. And since we're only 20 minutes into this, might as well. I mean, this is just about everything there is for the AND gate. Might as well get into the OR gate, and which should get you ready for Digital Logic Lab, which I believe starts this week. Let's see here. The OR gate has this curved on the back and is kind of like an arrow. That's the symbol for it. Again, A and B is the inputs, and out over here. When it comes to doing schematics, the convention is to put the inputs on the left and outputs on the right. So you follow the inputs to the outputs like you would reading in English. Not how you would read in Arabic or Hebrew. That's right to left. So, but the state table, The state table has both inputs being low leads to a low output, and any of the inputs being high leads to a high output. This is expressed in Boolean expressions as A plus B. And if you look at the binary, it almost looks like addition. Except for here. That's the only difference. Zero plus zero is 0. 0 plus 1 is 1. 1 plus 0 is 1. But 1 plus 1 is actually 2, but for the OR gate, it is a 1. When we get into adders later on in the semester, we'll see how you deal with adding and carrying a 1 into the next column. But the OR gate is often used. Let's go ahead and do the schematic of this. Let's see here. See if I can do this right. That's the basic idea behind the OR gate. The AND gate had the two input transistors in series. Here they're in parallel. So it behaves differently. So if any of these are high, if the A or B is high, then this is pulled to ground, either through the A transistor or the B transistor will be pulled to ground. This will be low here, and then this is the inverter, and this will be output to be high. So, and the chip that you'll be using, the 7432, if I'm recalling correctly, The pinout for the chip is like so. Another 14 pin dual inline package integrated circuit. Now, where you see the OR gate a lot is in combining outputs. If two logic blocks need to be combined together, they're typically done with an OR gate. So, for example, let's just go in here a little bit. If you have A and B, or B and C, you would have A and B, like so. You start on the left-hand side of the schematic with the innermost parentheses, and then work your way out of the parentheses and to the right. So that's how you would link them together in this particular situation. 3-input AND gate, should have led with this one. I mean OR gate, sorry, is similar to the AND gate. You just link them together like so. You can link them together however many you need, however many expressions you need to OR together. Now, linking the might as well cover this one now. Yes, this is an OR gate at the end, and as well as this. Yeah. It has the curve here and kind of a curved arrow to the right. Now, to do the addition, we'll kind of get ahead of things. If you have or let's see here, A or B, and not A and B, what would the state table look like for that? For those that took discrete structures last semester, should know, should remember something along these lines. So if you have this A and B, let's follow the traces through the circuit here. So low and low, low, low. With the OR gate, that would be low. AND gate would be also low. After the inverter, that would be high. So that would be low and high on an AND gate, which would be low. Right? See how I got that? If A and B are both low, going into the OR gate, that would be a low, right? Because the state table for the low gate, or for the OR gate. So that would be low here, and then obviously here. The state table for the OR gate. We're doing all the combinations. We're starting with this one. Yeah. So low and low make low on the OR gate. These connections here, this dot means that there's a connection between this line and this line. That is not a connection. So you have A is low, B is low. In an AND gate, from the state table, that's also low, so that's low on that end. Going through an inverter, that would be high, turn to high. So the inputs for this AND gate here are low and high, which from the state table of the AND gate is going to be a low. So the output would be low. All right. Now next, we'll do low and high. Low and high. So low and high. One of them is high, so the output of the OR gate will be high because A is low, B is high, output's high. Both inputs are not high, so this AND gate will also be low. Going through the inverter, that'll turn that to high. And then you have your two high inputs for the AND gate, which will make the output high. Follow that? Okay. So that would be high. Same thing happens with high and low. Makes that high, makes that low, high and high, high. I did do H, didn't I?
Oh, yeah.
Yeah. And then if you put both these high, the OR gate will be high. The AND gate this AND gate will also be high, making this low. And then the high and low in the AND gate would be low, making the final output be low. And this is an XOR gate. Exclusively OR. It is only high when one or the other is high, but not both of them. So that is an exclusive OR. Like I said, we touched on this briefly in discrete structures last semester, for those of you who took it. Kind of a little aside, you can get exclusive OR gates in chips. I don't remember the part number for them, but you can get them. What you can also do is add an inverter to this, and it inverts the outputs. To make what's called an exclusive NOR gate. Where this has an interesting property of if A and B match, high or low, the output is high. So if you have a series of bits and you want to compare bits or values, binary values, you can use the exclusive NOR gate, and if it's high, they match. If it's low, then A and B are different. The exclusive OR gate has the symbol and the exclusive NOR the exclusive is denoted by the extra line out the front, and NOR is inverted output with the bubble on the output. That's for, like I said, comparing bits. The exclusive OR is also used in another area where if you want to selectively invert a bit. Yes? This right here? That's the exclusive OR. Yeah. Yeah. I'm sorry? Yes. It just has the inverter on after it. The exclusive NOR you have to create. They do not make, in the 7400 series, exclusive NOR gates in a package. They don't exist. You have to make them like this, or there's another way that I'll show you later when we get into NAND and NOR gates. But right now, this is what we got. But let's see here. Next week, or next session, on Friday, we will get into the NAND and NOR gates, which are universal gates. You can use just NAND gates or just NOR gates to create any logical circuit. Have a good day. See you on Friday.